if we break a task into smaller tasks, then that job can be finished quickly. So parallelization can improve the performance of the applications. So if an application is implemented in such a way that it has multiple computing entities, then each task can perform a small part of that job. And these computing entities can run in parallel if that is supported by the hardware. For example, graphic processing units can perform thousands of tasks in parallel. So an application can be implemented with several threads, and these threads are the small computing entities which will perform a small part of the job. So they are very similar to processes, but they are lightweight processes. Why they are lightweight, we will see in a few seconds. This thread is also a basic unit of CPU utilization, and it helps in achieving parallelization. Now, we have been seeing till now, when we have been looking at the processes, that a traditional process had a single thread of control. That means all the instructions were being executed by a single processing entity. But if that particular process can be broken down into subtasks through multiple threads of control, then it can perform more than one task at a time. For example, take an example of a web browser. One thread can be used for the display and another thread can be used for retrieving the data that has been requested by the user. For a word processor, one thread is used for display, another thread can be used to respond to the user input through the keyboard, and another thread can run in the background to perform a spell check or a grammar check. Threads can also be used for the sorting algorithms, trees and graph algorithms as well. So use of multiple threads will break down the task and that job can be completed in a quick manner. So here is an example of a single threaded process. The process has a set of code, data and the files, and it is using some hardware like the registers, the program counter and the stack. And this single thread of control runs or executes the instructions using these resources. For a multi-threaded process, there can be multiple threads which will be sharing the same code, data and the files. But each thread will have its own set of registers, stack and the program counter. So while they are sharing few resources, there would be some resources which would be particular or specific to a thread. So a thread comprises of a thread ID. Just like a process has a process ID, each thread that is being created will have a thread ID. It has its own program counter, its own register set and its own stack. But as we have just seen, what it will share with the other threads of the same process is the code section, data section and some other resources such as open files and signals. So as we have seen over here, the code, the data and the open files, they are shared amongst all the threads of the same process, while each thread will have its own register set, its own program counter and its own stack. Here is an example of a multi-threaded server architecture. So if there is any client which sends a request to a server, the server will create a thread and this thread will service the request. Meantime, another thread or the main module of the server will keep on listening for additional client request. If another request comes, another thread will be created to process that particular request. Earlier, when threads were not being used, process creation was the method which was commonly used. But each time we create a new process, that is time consuming and resource intensive because no resources are shared when multiple processes are created, whereas threads can share resources. And if a new process that is being created it will be performing the same task as an already existing process, then why should overheads be incurred? So threads are a better option for this. So what are the benefits of having threads? First is responsiveness, that even if a part of the process is blocked, so if a process is there which has multiple threads, and if one thread has made a system call and due to which that part of the process is blocked, other threads can continue doing the other part of the process. So other jobs of the process, they can be continued even if one subtask is currently blocked. So this is important for user interface. So if one service is being processed by a particular thread and it has blocked waiting for input or output, other threads can still continuing to listen to user requests. Second is resource sharing. As we have seen, the resources are being shared between the threads. So this allows the threads to share, because they are sharing data. So the communication between the threads is easier as compared to the communication between processes, because if you look at the lecture on inter-process communication, shared memory or message passing is used. But threads are sharing open files and data, so resource sharing is better over here. Also, threads are economical for creating because they are much cheaper and the overheads involved are less. Also, the context switching between the threads is faster than context switching between the processes. So because of all these reasons, threads are known as lightweight processes. Threads can also take advantage of multi-core architecture. So if one thread is running on one core, another thread can be scheduled on another core. Now let us see two terms which are commonly used in multi-core programming. One is concurrency and the other is parallelism. Concurrency means that more than one task is being supported and they are making progress. So suppose if we have a single core architecture, so the scheduler will schedule one thread, then it will schedule another thread T2, then it will schedule another thread T3, T4 and so on. So all the tasks are being scheduled, each task is making some progress, but the core is single. Parallelism means that more than one task can be performed simultaneously. So there are multi-core architectures. On one core, we are running threads T1 and T3. So they are being scheduled. And on another core, another threads are running, T2 and T4 are running and they are being scheduled by the scheduler. So this is the difference between concurrency and parallelism. Then parallelism can be achieved in two ways. One is data parallelism and the other is the task parallelism. So what is data parallelism? That means on the same data, same operation has to be performed on like a large amount of data. So now this data can be broken down into chunks and each chunk or each subset of the data can be sent to different cores and each core will perform the same operation on each subset of the data. So this is data parallelism. What is task parallelism? Here each thread performs a unique operation. That means the data is same. This whole set of data is being sent to the different cores and each core is performing a different task on this data. So the data remains common over here and the task that is performed on that data is different and each thread over here will perform a different task on the same data.